construct in order to apply Gauss's law. So I'm going to create a cylinder here, a Gaussian cylinder, more specifically.
Gauss is just boosting his ego with all this.
Really?
Well, there's the riddle slash joke slash, you never laugh out loud at it, the greatest father-son math pair ever, greatest contribution, Gauss and his father. What did his father do?
Nothing.
It doesn't matter.
Yeah.
The greatest set of brothers, the most home runs. Anyone know the brothers with the most home runs?
Gauss and his brother?
No, I don't think he played baseball. Hank Aaron and his brother, Tommy Aaron. I think Tommy Aaron had like 30 home runs in his major league career.
And the other had 0?
No, he had 70 or 55.
Yeah, he did have the record. I think it's been passed. Hank Aaron definitely has the non-steroid record.
Yep.
All right, so basically I'm creating a cylinder around this line. The cylinder does not really exist. This is a virtual surface, and specifically a Gaussian surface, or even more specifically, a Gaussian cylinder. I can make the Gaussian surface of whatever shape I want. Cylinder just happens to be a nice, convenient object to use for a line. And what I want to do is I want to find the electric field at this point right here. So this is my point P. I want to find the electric field at point P. The cylinder has a radius of whatever the distance is from the line to where P is, so I'm going to use R for that distance. So R is the distance from the line to where point P is, and also the radius of my cylinder. And this length here is length L. Don't worry, L is going to go away at some point. Because if it didn't, then we'd be in trouble. And it'd be a useless technique. Now, not really a hand wave in physics. In math class, this would be called or a hand wave. But in physics, we make an argument by symmetry. I know that the electric field has to be pointing away from the line. The electric field has to be going that way. Or down here, be going that way, or out here, be going that way. It is perpendicular, pointing away from the line in a perpendicular direction. Because if I have a line of charge here, and I'm looking at the electric field at this point, the electric field at this point is just the sum of the electric field from all these points here. So there's a point on the line here, charge on the line here, creating an electric field going in that direction. It wasn't supposed to bend like that, but going in that direction. And I got one over here going in that direction. For every, that's sort of the close point, for every point over here, I've got one on the other side, which is basically symmetric. So all components of the electric field that are horizontal in the way I've drawn it are going to cancel out. The only components of the electric field that will remain are vertical. So I know the electric field has to be pointing away from the line. So no matter where I am, electric field is pointing away. Questions here before we apply Gauss's law? All right. I know that the total electric flux through a closed surface is equal to the enclosed charge divided by epsilon sub naught. This would be the, since it's a closed surface, this is the electric field through, well, basically got three surfaces here. I got my left end, so this side over here, plus that would be the electric field from the right end, plus, well, I got the main body of the can, plus the electric field from the, I'll just say main body. And that's going to be equal to my enclosed charge over epsilon sub 0. And here's the convenience. What's equal to 0?
Left end plus the right end?
Why?
They seem like they would be opposing each other.
Not the reason. They do go to 0, but not for that reason.
Equal in magnitude, opposite in direction was my thought. Is that not what it is?
That is not.
Because they're like, the lines are going parallel or perpendicular off of this line, right? And so are they, so there's no.
Closer. What's the formula for electric flux? Through a surface. Not a closed surface, but just a surface.
The sum of E, like, the sum of E, times A.
Right, E dot A. So on the left surface here, let's take this side, which way is the area vector pointing? Ooh,
Wait,
Really?
oh,
The surface over here.
On the cylinder.
Is that parallel
Yes.
to the line?
say it again? You said along the line?
Parallel, oh, but it has to be this direction.
Yeah.
I-
The area vector is pointing that way, again, away from the inside.
Oh, right, because
The electric field going that way, or, basically anywhere around here.
Right.
And keep going, but my arm doesn't bend so far. So they are perpendicular. The area vector and the electric field are perpendicular no matter where I am on here. Yes, dot product is 0. So that's 0 because my electric field is perpendicular to the area vector for the left side. And that's 0 for the same reason except for the right side. So all I'm left with the electric field around the main body. Which is convenient because at this point right here, what's the direction of the area vector? And at this point, what's the direction of the area vector? Hey, same as the electric field. When I'm out here in front, which way is the area vector? Same as the electric field. The electric field and the area vector are always in the same direction no matter where I am on the cylinder. So E dot A is just the electric field times the area. And that's equal to my enclosed charge divided by epsilon so naught. So let's actually narrow that down just a little bit. I know that lambda is charge divided by length. So therefore a charge would be lambda times the length. Just multiply both sides by L. So now we have over here lambda L over epsilon sub naught. So this is the area of the main body. I guess I'll write down main here. So what is the area of the side of the cylinder?
Wherever the area of like a circle is, and then point it out in that direction.
Does it involve the formula of like an area of a cylinder, like the
I mean,
pi- I'm thinking like, what is it, like pi squared times the length, like that's.
Is that what you were going for? Yeah, so that would actually be the volume of the cylinder. We need surface area.
And we just need the surface area.
It's basically a rectangle, it's just
Yeah.
connecting to the
Yeah. So if you think about it like this is the part, we don't care about the ends, we just care about the mid-body. So if we think about it as a rectangle opened up, I know that this length here is L.
So the circumference of the circle times L.
And what's the circumference of a circle?
2 pi r?
Usually without the question mark, but yes. So this becomes E times 2 pi r L is equal to lambda L over epsilon sub naught. And the length cancels out. Who would have thought? So my electric field strength, the magnitude of my electric field, this E right here, is lambda over 2 pi epsilon sub naught r. And away from line. Oh, bad notation there. The magnitude doesn't have a direction.
It's just any direction away from line, right?
Yeah, the direction would be anywhere away from the line. And perpendicular to the line.
What are our units? Wait,
Units of,
the electric, oh, is it just Coulomb? Of the electric field?
newtons per coulomb. And we can verify that. This right here, this lambda is charge per unit length. So our units would be coulombs per meter. We have R here, which is meters. And then we have epsilon sub naught on the bottom, which is a coulomb squared per Newton meter squared. Meters cancel out, that coulomb cancels out with one of those. I'm dividing by a fraction, so that just becomes newtons per coulomb.
Could you go over again why I know that they're perpendicular E and A. Could you go over why we get rid of those? I know the answer might be because they're perpendicular, but.
Because if the electric flux through a surface is E dot A. And it's the nature of what a dot product tells us.
Okay.
The fact that,
And so since it's a dot product, they're perpendicular, and so it's zero?
yes,
Okay.
yeah.
Okay.
It just mathematically, they define electric flux this way.
Okay.
Name them.
Avoid them. Them like to make things difficult for me.
Oh. Questions? Or other questions?
When we drew the Gaussian cylinder, did it matter whether it was a shell or a solid cylinder? It seemed like we were just dealing with the surface.
It is the Gaussian, it's a Gaussian surface, so it has to be a closed shape. And in essence, hollow inside.
Right, okay.
But the ends of it wouldn't matter, cause it's just a surface, right?
Wait, say it
Like
again?
the ends of that cylinder, like the two circles on either end, those wouldn't matter though, cause it's just.
In our particular case here.
Yeah.
We're about to do one where they do matter.
Okay.
All right, let's do the other one. So we did the infinite line, we've done the sphere. Now it's time for the infinite surface, the infinite plane, I should say. Infinite plane. With uniform surface charge density. Sigma. Now, most textbooks that I run across use sigma for this. The textbook that I was using for 252, the prior one, they used the eta. So I mean, it does change. If you're looking at other sources, just don't be shocked if suddenly they're using a different Greek letter. But lambda, generally line begins with an L, lambda begins with an L. Let's use lambda for that. Surface begins with an S, sigma begins with an S. Let's do that. And then rho. So my surface, my Gaussian surface this time is from a side view. So this is the jaunty tilt view. And side view. I want to find the electric field at this point. Actually, let's make it a little bit bigger. This point here. What is the electric field at this point? This is an infinite plane. I'm going to create my Gaussian surface so that it extends to here and back on the other side. From a side view, it's a cylinder. I'm taking a cylinder, I've got two cans here, and I've got a piece of paper trapped between them. So this is round on this end, it's round on that end. Surface charge density is charge divided by area. So my charge would be area times whatever the density is. I'm going to use some of the writing I've done before, for better or for worse. it's still a cylinder, and I got two ends and I got the main body, so this still holds true for this particular Gaussian surface. From a symmetry argument, which way will the electric field be pointing at point P? Let's say in this drawing right here, instead of the jaunty tilt one. Which way will the electric field be pointing here at this point? And why?
To the right because, you said earlier that, if this is uniform, which you said it is, then all of the charges on that line will all like cancel each other out except for the one that's like directly in the middle, that's perpendicular.
Absolutely. So, if you want to do the physics answer to it, when I said why, it would be by symmetry.
Because I said.
As if, not because you say so, but say by symmetry and then look at me like I'm a moron.
Okay.
All right, so my electric field would be pointing away no matter where I am because it's an infinite plane. All right, so which of these will be zero?
Is it similar to the last one we did where it's like where it like on the left side and on the left end and the right end it would be 0? Wait.
You said similar. I could make an argument that yes, it's similar, but it depends on how similar you're going to make them. It's not that exact.
Hold on. I'm gonna think about it for a second.
All right, so what's the direction of the area vector? Let's go for a different color because that just pops on video. Only I had yellow. All right, what's the direction of the area vector here? On the right end. It's got to be, since this is a closed surface, even though it's virtual, it's still a closed surface, the area vector has to be pointing toward the outside, and it's perpendicular. What about the top part of this central one? And what about over here?
Let's go to the left. So we'll cancel out on the left end and the right end.
No.
Wait, no, because it's parallel. No.
Yeah, the parallel here, so we'll multiply together to get some positive number, and some positive number over here.
So I guess it's the main body that cancels out because that would be perpendicular.
Yes. Area, no matter where I am on the surface of the main part of the body, it is going to be pointing parallel to the plane or perpendicular to the surface, and the area vector, the electric field is definitely pointing that way. So no matter where the area vector is on the main body, they're perpendicular. So that's 0 this time. My left end is just going to be E. It's supposed to be a capital E there. E times my area vector,
Which is infinite.
which is
Infinite.
no. Oh, I guess I need to give one more dimension here. Let's make the radius of this R. No, my Gaussian surface here is definitely finite shape, finite size. That length R there, there's some length in this direction, but I really don't care about that one. What is the area of my left end or right end?
2 pi r?
The other one.
Pi squared.
Pi squared, yeah.
Yep, that's it. So this is E times pi R squared. Plus, over here, it's the same area, E times pi R squared, plus 0, is equal to my enclosed charge, which is just my area times sigma. It's the area here in the middle, which is the same area as the left and the same area as the right. I have a regular cylinder here, I'm not tapering it, because that would be insane if I wanted to do that. Okay, perhaps not insane, it would be a waste of time. So this is pi r squared times sigma over epsilon sub naught. And usually a subscript, not a superscript. Everything's got pi r squared, that's convenient. So I'm left with 2 times the electric field strength is equal to sigma over epsilon sub naught. or the magnitude of my electric field is equal to sigma over 2 epsilon sum naught. Recognize what is missing.
Direction?
We don't need it because it's magnitude.
All right, we don't have direction because it was just magnitude, but we could put that in there. It's away from the plane, whichever side you're on.
I said units.
Units would be mixed in with the, when we put numbers in, we'd have to have units. But we've got to get newtons per coulomb in the end. But in terms of what's missing, I got my infinite plane here. What's the relationship between the electric field at point P and the electric field here at point, we'll just call it P2, which has a larger electric field?
It should be the same.
Yep. The distance from the plane is irrelevant. If you had this infinite sized wall in front of you and you were looking at it, since this is a make-believe thing, your universe consists of this infinite plane and you, and you're looking at this, you cannot tell how close you are to it. There's absolutely no depth of field in a sense, because no matter how close or far away you are, it still looks the same. And this gives us an incredible, this formula right here makes capacitors really, really doable. If I have an infinite plane here and an infinite plane here, let's say that this has a positive surface charge density and this has a negative surface charge density, same magnitude, just opposite directions, or opposite signs. What is the direction of the electric field from the positive plate here?
What is, sorry. did
The
you-
direction of the electric field from the positive plate at this point where my finger is.
We're assuming.
Okay?
Assuming it's a neutral charge? The point?
No, it's got some charge. The surface charge density.
Right, but the point itself is neutral.
Oh, there's nothing at this point. It's just, electric field doesn't need anything there.
Right.
All right, so it goes in that direction. What about